Chebyshev's inequality was to have a very deep consequence right across the theory, but it immediately provides us a vehicle to analyze and understand why poles really work. So let us begin with a quick recapitulation of what the essence of a pole is. We imagine an underlying population which has individuals of two types, 1 or 0, Republican or Democrat. These subpopulations appear in a proportion P and a proportion Q that are a priori unknown to us. We wish to understand what the distribution of these proportions is. In other words, we'd like to estimate P and Q. To this end, we start by sampling randomly, independently, without bias from the entire population. Recall that sampling is, at least nominally, with replacement, and we engender a random sample of size n. x1 through xn correspond to Bernoulli trials with a fixed but unknown success probability p. And naturally, we immediately form an accumulated sum of successes in the sample, and this is what we call S sub n. Of course, S sub n is equipped with a binomial distribution with two parameters, a number of trials n, the number of times we've tossed this metaphorical coin, and the bias parameter p representing the subpopulation proportion that we are interested in estimating. Bear in mind that once we generate a sample, we know n. Of course, this is the number of data points we have accumulated, but we do not know p. We have been led to believe that the estimate of the relative frequency of successes in the sample, S sub n divided by n, is indeed a good estimate of the underlying population proportion p. How good is it? So, here's a stage where we first realize that it's a chance experiment, so certainty is going to be elusive. We are going to be, perforce, compelled to make errors, but we'd like to control the size of the errors. It's a chance experiment, therefore we can't have certainty, so we're going to have to say things with a certain amount of confidence. And so the error we make, the confidence with which we make a pronouncement, and the sample size are intimately connected. What is the desideratum? That our estimate of p, in other words, the relative frequency of successes, Sn over n, deviates from the fixed underlying subpopulation proportion p, but even a small amount, epsilon, the error tolerance. This probability should not exceed a number delta, where 1 minus delta is the confidence we wish to have. For definiteness, we could think of, say, epsilon a small number, say 3%. Delta is another small number, say 5%. So we want no more than a 3% error with a confidence of 95%. It's a very simple, beautiful, elegant equation, and its estimation is facilitated by Chebyshev's inequality. The probability at hand is bounded above by the reciprocal of 4 times the sample size n times the square of the error parameter epsilon. And so it suffices if this bound is no more than delta. And so we have a slogan. If the sample size exceeds the reciprocal of 4 epsilon squared delta, then we can assert that our estimate of the underlying population proportion p has made an error which is no larger than epsilon with a confidence of at least 1 minus delta. Some numerical estimates will add flesh and color to these bare mathematical bones. So let's go ahead and promptly plug in some numbers. Suppose we look at a situation where we are permitted to make no more than, say, a 10% error. And we want a confidence of at least 90% in our pronouncement. We plug in epsilon is 0.1, delta is 0.1, and we observe that the sample size that is requisite is 250. What if we want a tighter error tolerance, say 5%, epsilon is 0.05, and say we want a tighter confidence. We want a confidence in our pronouncement that of at least 95%. In other words, delta is also 5%. Plug in epsilon and delta both being 0.05, and we find that a sample size of 2000 suffices to guarantee an error of no more than 5% with a confidence of at least 95%. And if we get a little greedier still, an error of 3% and a confidence of 95%, epsilon is 0.03, delta is 0.05, and now we find that a sample size a little in excess of 5,500 will suffice to give us a fairly small error of no more than 3% with a high confidence of at least 95%. There's something that are worth taking stock here. Observe that our sample size estimate for a desired error tolerance and for a desired confidence, our sample size estimate nowhere contains within it the size of the underlying population. It is independent of how small or large the underlying population is. It makes no matter whether we are dealing with a population of 10,000 or 100,000, a million, 10 million, or a billion. Whatever the size of the underlying population, if it is dichotomous and contains subpopulations of two species, two types, two characters, two colors, a fixed sample of size about 5,500 will estimate the relative sizes of these subpopulations with an error of no more than 3% and a confidence in excess of 95%. This is magic. And of course, we should promptly encapsulate it in these political days via a slogan. So here's our slogan. A relatively small, honest, random sample. What does honesty mean here? That, in fact, the sample is independent and that it is unbiased. A relatively small sample of the order of a few thousands, whose size does not depend upon the underlying size of the population or upon what the particular mix of subpopulations is, what P is. So a sample size independent of these parameters gives a very good estimate of the underlying subpopulation proportions. This is magic of a high order. And this is why polls work. On the face of it, they have no business working. A sample of a size of a few thousands doesn't seem reasonable that it would contain within it the sentiments of a very large underlying population, but it does. And at the heart of all of this is the inequality of Chebyshev.